There's a star in our own galaxy that refuses to play by the rules. It's not the brightest, not the hottest, and definitely not the calmest. Instead, it spins faster than any engine we've ever built, a cosmic blur tearing through space, and it's so dense that a single teaspoon of its material would outweigh an entire mountain. But the real nightmare? It's unstable, constantly on the verge of collapse. Just a bit more mass, a bit more pressure, and this thing could implode into something far worse. A black hole. And the scariest part? It's not hiding in some far-off corner of the universe. It's right here, in our own Milky Way. Spinning, feeding, growing. Scientists have tracked it for years. They've even named it. But despite all the data, one question still haunts them. When will it finally collapse? Or maybe, has it already? When a massive star dies, it doesn't fade away. It fights. Every last bit of fuel burns in a desperate battle against gravity. But when the fire dies, gravity wins. The core caves in. The outer layers blast out in a massive supernova. And what remains is something beyond strange, tiny, dense, and terrifyingly heavy. That remnant is a neutron star, not just dead, reborn into something monstrous. Most are no bigger than a city, maybe 20 kilometers across. You could cross it in minutes if you somehow survived the crushing gravity and blistering radiation waiting on its surface. Imagine squeezing everything in our solar system, every planet, mountain, ocean, and person, into a ball the size of Manhattan. That's what a neutron star is like. It's so compact, so impossibly dense, that a single teaspoon of its material would weigh more than 1 billion tons, heavier than every skyscraper in New York City combined. Drop a sugar cube-sized piece of it onto Earth, and it wouldn't stop at the surface. It would punch straight through the crust, tear through the mantle, and keep going until it reached the core, without even slowing down. But that's only the start of its madness. Some neutron stars spin, and not slowly like Earth. They rotate so insanely fast that they shoot beams of energy into space, sweeping around like the light of a cosmic lighthouse. Those are called pulsars. The name doesn't come from a heartbeat, but from how those beams flash past us in perfect rhythm, appearing as repeating pulses of light or radio waves. When Jocelyn Bell Burnell first detected one in 1967, the signals were so precise that her team briefly thought it might be aliens. Something in deep space was ticking with atomic clock precision. But the truth turned out to be even stranger. These stellar engines can spin hundreds of times per second, faster than helicopter blades, faster than any blender, and in some cases, faster than a jet turbine. They're cosmic flywheels, spinning endlessly in the dark, powered by the most extreme physics in the universe. Some pulsars have been spinning for millions of years without slowing down, locked in motion by their insane angular momentum and near-perfect efficiency. But that's where things start getting dangerous. Because not all of them drift alone in space. Some find themselves in twisted relationships with other stars. Deadly partnerships born from gravity's grip. Through a process called accretion, these pulsars start stealing. They drag material off their companion stars, pulling it into a blazing whirlpool of plasma that spirals straight onto their surface. Each stream of stolen gas makes the pulsar spin faster, burn hotter, and grow heavier. Scientists call these monsters Black Widow pulsars, and the name fits perfectly. Just like the spider, they devour their partners after the act is done. The unlucky companion is stripped layer by layer, atom by atom, until there's almost nothing left. But this cannibalism can't last forever. There's a limit, a point where the neutron star simply can't take on more mass. When that threshold is crossed, the internal pressure collapses. The pulsar's structure gives way, gravity wins, and the whole thing implodes into a black hole. So when scientists call these stars dangerous, it's not because they're about to explode. It's because they're already ticking time bombs, dense, unstable, and ready to fall in on themselves at any moment. And the one we're watching? It's no ordinary pulsar. It's the fastest spinning, heaviest neutron star ever found, lurking right here in our own galactic neighborhood. What makes it so different? Well, not all pulsars play by the same rules. Most neutron stars are already monsters, dense, powerful, and terrifyingly compact. But every once in a while, astronomers find one that doesn't just break the rules. It rewrites them. One of those cosmic anomalies is PSR J0952-0607. It's not a catchy name, and it's not from a sci-fi movie. But its stats read like a galactic hazard warning. This thing spins 707 times per second. That's not an exaggeration. 700 full rotations every single second. You couldn't even blink fast enough to keep up. Its surface is moving at a huge fraction of light speed, yet it doesn't tear itself apart. Gravity keeps everything locked in, compressing the star so tightly that atoms can't even exist anymore. What's left is pure neutron matter, a sea of subatomic particles crushed beyond imagination. And as if that wasn't enough, this is also the heaviest neutron star ever found. Nearly 2.4 times the mass of our Sun, squeezed into a sphere barely 20 kilometers wide. That combination of extreme spin and near-limit mass makes it dangerously unstable. You see, neutron stars aren't supposed to get that heavy. The Tolman-Oppenheimer-Volkoff limit, the theoretical maximum, sits somewhere between 2.5 and 3 solar masses. Cross that line, and the star can't resist gravity anymore. It collapses straight into a black hole. This one is right on that edge, and the reason it got there is hauntingly simple. It ate its way up. Orbiting nearby is the shredded corpse of what used to be a normal star, now just a dim white dwarf, slowly being ripped apart. Its gas spirals toward the pulsar, some of it swallowed whole, the rest forming a glowing accretion disk. Either way, the neutron star keeps feeding, growing, and inching closer to the point of no return. As the pulsar keeps feeding, it also keeps spinning faster, like a figure skater pulling in their arms. The smaller it gets, the faster it turns. Each stolen gram of matter doesn't just add weight, it adds tension, pressure, and danger. Every bite it takes brings it one step closer to collapse. That's why astronomers call this kind of system a black widow pulsar. It drains its partner until there's nothing left. The white dwarf fades away. The pulsar grows heavier and hungrier, until all that remains is one unstable, overfed star teetering on the edge of destruction. And here's the terrifying part. If it does collapse, we might not even notice at first. Unlike a supernova that bursts across the sky with brilliant light, this kind of death happens quietly. There'd be no flash, no shockwave, no fireworks, just silence. The rhythmic pulses that have traveled across space for thousands of years would suddenly stop, and in that quiet, a black hole would be born. No one knows when that moment will come. Maybe 1,000,000 years from now. Maybe tomorrow. Or maybe it's already happened, and we're just waiting for the signal to reach us from 14,000 light years away. And remember, this isn't some distant object at the edge of the universe. It's inside our own galaxy, spinning at full throttle in the Milky Way. A cosmic time bomb, held together by nothing but speed and luck. That furious spin is the only thing keeping it from collapsing, buying it time in a losing battle. But eventually that time runs out. When it does, there's no explosion, no grand finale. Just a sudden, complete collapse. 1 second it's a pulsar, beaming, flashing, alive. And the next, it's gone. The light vanishes. The radio waves stop. A galactic lighthouse, switched off forever. What's left behind after that silent collapse is a black hole. And this is where the real physics begins. Unlike a supernova that rips itself apart in a blinding explosion, a pulsar's collapse is quiet and clean. There's no outer layer to blast away, no debris to scatter across space. The matter is already crushed to its limit, so when it gives in to gravity, the transition is instant and absolute. The mass remains, but it's hidden, trapped behind an event horizon, where gravity becomes so intense that not even light can escape. From the outside, it simply disappears, leaving behind a dark void that bends space and time around it. Near its edge, time slows, light bends, and anything that drifts too close is doomed to fall in. Now, here's the good news. If this collapse happened tomorrow, we'd never notice, at least not for another 14,000 years. That's how far away this pulsar is from Earth. The light and radio waves we detect right now are ancient, a snapshot of how it looked 14 millennia ago. For all we know, it might have already turned into a black hole, and we're just waiting for the universe to deliver the update. But if it has collapsed, the story doesn't end there. Its surroundings would erupt in chaos. The magnetic fields and leftover plasma swirling in the accretion disk would keep feeding the newborn black hole, still spinning, still charged with energy. That violent feeding can launch relativistic jets, massive beams of particles and radiation, fired from the poles at nearly the speed of light. For a brief, blinding moment, the galaxy would host one of the most powerful engines in the universe, a newborn black hole announcing its arrival in silence and fury. If those powerful jets ever happened to point even slightly in our direction, even from 14,000 light-years away, the results could be catastrophic. And that's not a theory. Scientists like Adrian Malott and Brian C. Thomas believe that one of Earth's ancient mass extinctions, around 440 million years ago, during the late Ordovician period, may have been triggered by a gamma-ray burst from a nearby neutron star or black hole. It wouldn't have been an explosion we could see or hear. Instead, it would have quietly stripped away our planet's ozone layer, leaving the surface naked to deadly ultraviolet radiation from the sun. The aftermath? A chain reaction of dying ecosystems, collapsing food webs, and oceans teeming with extinction. Now, the odds of that happening again, and of this pulsar's jets being aimed at us, are extremely low. Space is vast, and most of these jets shoot off in random directions. Still, the possibility is enough to keep astronomers watching closely. But let's turn the question around. What if the collapse doesn't happen all at once? What if the pulsar just keeps growing, pulling in more mass, building pressure, and inching closer to that breaking point while still spinning at 707 rotations per second? Eventually, even that speed won't save it. When the balance breaks, the star could collapse in an instant, releasing a sudden, powerful burst of gravitational waves, ripples in the very fabric of space-time. Instruments like LIGO and Virgo might detect that pulse, capturing the precise moment when a neutron star transforms into a black hole. It would be a first in human history, a silent death broadcast through gravity itself. One of the fastest, densest, most extreme stars in the Milky Way, gone forever. No light, no pulse, just a dark void where a cosmic heartbeat once echoed. From a cosmic point of view, that pulsar's collapse might seem like the end of the story. But for us, it's just the beginning. Because there's another kind of neutron star out there, one that doesn't need to collapse or spin at record-breaking speeds to be deadly. It doesn't have to consume its neighbors or blaze across space with radiation beams. It's quiet, magnetic, and terrifying. You'd think a star spinning hundreds of times per second and holding more mass than the sun would be the ultimate danger. But nature, as always, finds a way to go further. Enter the magnetar, a neutron star so extreme it doesn't just bend physics, it breaks it. Take everything that makes a normal neutron star horrifying, the density, gravity, and compactness, then multiply it by a magnetic field so powerful it can literally tear atoms apart. Not just ionize them or strip their electrons, but destroy the very bonds that hold matter together. A typical pulsar's magnetic field is already trillions of times stronger than Earth's. A magnetar takes that number and turns it up another 1,000-fold, reaching over a quadrillion times stronger than Earth's field. At that strength, chemistry stops working. Get anywhere near one, even thousands of kilometers away, and your atoms would simply disintegrate. And this isn't just theoretical. We've seen what they can do. In 2004, a magnetar called SGR 1806-20, located about 42,000 light-years away in the constellation Sagittarius, unleashed a burst of gamma radiation so intense that it overloaded satellite sensors, even from across the galaxy. For a brief instant, it became one of the brightest sources of energy ever recorded in our sky. If a magnetar like that were only a few light-years away, it wouldn't just overload satellites, it could strip away Earth's atmosphere. Magnetars don't need to move fast or feed on others to be deadly. They just exist, and that alone makes them some of the most dangerous objects in the universe. For a split second, that magnetar outshone every other X-ray source in the entire sky, combined. If it had been just 10 light-years closer, Earth could have been in serious danger. And this is where things start to get deeply unsettling. Unlike pulsars, which slowly spin down and fade, magnetars are unstable ticking bombs. Their magnetic fields twist and strain beneath a crust made of ultra-dense neutron matter. Eventually, that pressure becomes unbearable, and the star literally cracks. Scientists call it a starquake. Imagine an object the size of a city, but with more mass than the Sun, splitting open under its own stress. When the crust shifts, the magnetic field suddenly snaps and realigns, releasing more energy in a blink than all the nuclear weapons on Earth combined. These bursts of radiation travel across space at the speed of light, blasting out gamma rays and X-rays with the power of 100,000 suns. There's no warning, no rumble, just an instant flash of destruction. Thankfully, the closest known magnetar is around 8,000 light-years away, far enough that even a massive flare wouldn't hurt us. But if one were to erupt within 40 light-years, it could tear apart our ozone layer, flooding Earth's surface with lethal ultraviolet radiation. And here's the terrifying twist: magnetars don't live long. Their incredible magnetic power burns out quickly, fading within 10,000 to 100,000 years, a mere blink in cosmic time. That makes them rare, but not rare enough. For every 1,000 neutron stars, astronomers estimate that about 10 become magnetars. Even when they're calm, their fields distort everything nearby. Any planets unlucky enough to orbit them would be bathed in constant radiation, their atmospheres stripped away molecule by molecule. And if a flare ever erupted while a planet was close, the result would be instant sterilization, life erased in less than a heartbeat. You don't need a supernova or a black hole. All it takes is a crack in the crust, and it's game over. That's what makes magnetars a different kind of threat. They don't announce themselves with steady pulses. They don't ramp up with warning. They're like cosmic mines, sitting silent. And when the stress lines up just right, they detonate. So here's our lineup. Neutron stars that spin so fast they make fake lighthouses in space. Magnetars with the strongest magnetic fields in the universe. And at least one pulsar in our own galaxy riding the edge of collapse. Now for the obvious question, what if one of them wasn't far away? Everything so far sounds distant. 20,000 light-years, 50,000 light-years. Even the closest magnetars sit thousands of light-years out, tucked behind an ocean of space. That's why most people shrug it off. Danger feels small when it's far. So let's bring it closer. Imagine one neutron star. Doesn't matter if it's a pulsar, a black widow, or a full-blown magnetar, gets kicked our way. A supernova blast, a gravitational shove. Space is messy, and these objects move. Some neutron stars rocket along at over 1,500 kilometers per second, fast enough to leave the galaxy. Now picture one of those, maybe even PSR J0952-0607, drifting inside Jupiter's orbit. Say it parks about 500 million miles from Earth. Sounds distant, right? Jupiter distant. No big deal. Think again. First problem, gravity. Even from that range, the pull from a neutron star that massive would start tugging on the outer planets. Jupiter, Saturn, even Uranus could feel their orbits twist. Over time, those tiny shifts stack up and the whole system begins to wobble. The chaos creeps inward. Second problem, tides. A neutron star's gravity would create brutal tidal forces across the giant planets, stirring their interiors and reshaping their moons. Resonances would form, then break. Comets and asteroids long asleep in the cold could be thrown onto new paths, some aimed straight for the inner system. That's how a single star, still far away, turns the solar system into a slow-motion disaster, one nudge at a time. Then comes the radiation. A pulsar like J0952-0607 doesn't just spin, it fires. From its magnetic poles erupt twin beams of high-energy radiation made of X-rays, gamma rays, and charged particles. If Earth ever crossed the path of even one of those beams, we'd be in serious danger. At first, our magnetic field might shield us, briefly, but the onslaught would be too strong. The ozone layer would disintegrate, stripping away our first line of defense. Unfiltered ultraviolet light from the sun would begin sterilizing the surface, cooking everything exposed. High-energy particles would rip apart molecular bonds in the air, unraveling the chemistry of our atmosphere itself. Satellites would short-circuit, GPS systems would collapse, radio communication would fail. The night sky would blaze with unnatural light, and auroras, those calm, green polar ribbons, would stretch across the entire planet, flickering like a global warning sign. And if it wasn't a pulsar, but a magnetar heading our way, the rules get even darker. Magnetars don't need to spin fast or beam radiation to destroy. They just have to be close. Within a few thousand kilometers, their magnetic field could literally pull apart the atoms in your body, not by heat or radiation, but by raw magnetic force. Your molecules wouldn't burn. They'd simply unravel. Even from afar, say from the moon, the view would be horrific. Earth itself would start to deform under the neutron star's pull. Tides would surge and twist. The crust could shift, volcanoes would awaken, and pressure deep beneath the surface would explode into earthquakes that ripple across continents. Soon, the atmosphere would peel away, blown into space by radiation and magnetic interference. The oceans would rise, boil, and vanish. The ground would glow red with heat. Life wouldn't fade over centuries or decades. It would end in hours. And yet, for the neutron star, whether pulsar or magnetar, none of this would even register. To it, our extinction wouldn't be an act of violence, just another minor disturbance in the endless, indifferent void. To a neutron star, Earth would be nothing, just another rock drifting too close. Our sun wouldn't fare much better, barely a snack in its gravity well. If the star kept feeding, pulling in more material through an accretion disk, it could eventually collapse into a black hole right inside our solar system. From that point on, gravity would rule everything. Planetary orbits would unravel. The sun itself would spiral toward the event horizon, swallowed whole without a trace. And that would be the end. Not just of us, but of the entire system. Of course, the odds of that happening are almost zero. Space is huge. Neutron stars might be powerful, but they're scattered thin across the Milky Way. Even though there are hundreds of millions of them out there, the chance of one randomly drifting into our neighborhood is lower than winning the lottery every single day for 100 years straight. But that's not what makes them terrifying. What matters is that these things exist, they're real, and they're everywhere. Some spin faster than any human-built machine. Some emit beams of invisible, lethal radiation. Others have magnetic fields so strong they could destroy entire planets without ever touching them. And here's the strangest twist: a few of them actually have planets of their own. It sounds impossible, right? After everything we know about their gravity, radiation, and crushing magnetic forces, you'd think nothing could survive nearby. Certainly not something as delicate as a planet. But somehow, a handful have. Out of all known pulsars, roughly 0.5% have been found to host planetary systems. Tiny, fragile worlds orbiting one of the most violent types of stars in existence. Proof that even in the deadliest corners of the universe, something can still hold on. Out of the thousands of pulsars we've discovered, only a few have planets, and those rare cases raise one big, haunting question. How can a planetary system even survive around one of the most violent objects in the galaxy? Normally, planets form from leftover dust and gas orbiting a newborn star, the scraps of its creation. But a pulsar is born in total destruction. A massive supernova wipes everything clean, shredding planets, burning atmospheres, and blasting debris into space. What's left is a hyperdense core spinning like a blender, wrapped in magnetic fields strong enough to sterilize entire solar systems. So if a pulsar has planets, they weren't the originals. They either formed later from the wreckage or were captured long after the chaos ended. One of the strangest examples is PSR J0952 located about 2,300 light-years away. It made history in 1992 as not just the first pulsar with planets, but the first confirmed discovery of any exoplanets, period. This pulsar hosts 3 rocky worlds, all larger than Earth. What's bizarre is that despite the extreme environment, they orbit in relatively stable paths. Their orbits aren't smooth circles like our planets, but highly elliptical, swinging close and far as they loop around their radioactive parent. Given the pulsar's violent gravity, the fact that these planets even exist, let alone stay in orbit, defies reason. Now, imagine standing on one of them. There'd be no sunlight, no blue skies, no gentle warmth. The heavens would be pitch black, broken only by flashes of deadly radiation sweeping across the surface each time the pulsar's beam passes your world. Instead of dawn and dusk, you'd live under pulses of energy, bursts of invisible light that burn, twist, and warp everything they touch. A planet like that wouldn't orbit in peace. It would endure every second of its existence. On a pulsar planet, sunlight doesn't warm you, radiation kills you. The surface would be blasted by bursts of high-energy particles strong enough to sterilize everything in seconds. The only chance for life would be deep underground, hidden beneath miles of rock or sealed under layers of ice, maybe in dark subsurface oceans far from the deadly surface. Scientists have a few theories about how these impossible worlds form. One idea is that they're reborn from destruction, made of supernova debris that didn't escape into space. Over time, that leftover dust and gas could fall back toward the pulsar, forming a disk that cools and clumps into new rocky planets. Another theory says they're the remains of a companion star, ripped apart by the pulsar's gravity. The leftover fragments might compress and settle into orbit, cosmic scraps reshaped into new worlds. And then there's the wild card, captured planets. Rogue worlds drifting through interstellar space, caught by the pulsar's gravitational pull. It's rare, but not impossible, especially if the pulsar once had a binary partner that was destroyed, leaving behind loose planetary debris to trap passing objects. However they formed, these worlds are survivors. They've endured radiation storms, magnetic chaos, and violent gravity. And somehow they're still there, quietly orbiting death itself. Another example, PSR J0952 has at least 2 known planets, both several times more massive than Earth. One completes an orbit every 1.9 years, the other every 3.6 years. Their paths aren't smooth or calm, they're stretched, unstable, constantly shifting, like cars trying to steer through a cosmic hurricane. What's strangest of all is how little we actually know. We've only found pulsar planets around a few neutron stars, but that might be because they're nearly impossible to detect. There could be many more out there, hidden in the static of the cosmos. Tiny, haunted worlds circling the dead hearts of stars. After all, we're trying to detect tiny planets orbiting stars barely the size of a city from thousands of light years away, and somehow we've still found them. They're out there, and if life ever managed to evolve on one of these worlds, it would have to be something beyond imagination. Not just resistant to radiation, but designed for it, built to survive chaos, built to endure bursts of energy strong enough to melt entire atmospheres in minutes. Now, let's come home, to Earth. We orbit a calm, steady yellow star. Our magnetic field is gentle but protective. We breathe an atmosphere that shields us from deadly radiation. Water flows freely on the surface. In every sense, our solar system is quiet, unbelievably quiet compared to the violent neighborhoods out there. The fact that neutron stars can even host planets just makes it clearer how lucky we are. Against all odds, we exist in the rare calm between cosmic storms. And that brings us back to the question that started this story. The most dangerous star in our galaxy might explode any minute. Should we actually be worried? We've talked about stars that spin faster than jet engines, crush matter tighter than atomic nuclei, and shoot beams of radiation that could vaporize a planet. We've seen pulsars that devour their companions and magnetars that crack open like lightning-filled eggs, blasting radiation across space. It sounds like something straight out of a horror film. But here's the truth. No, we don't need to worry. Not in the way we think about danger. The pulsar PSR J0952-0607 isn't about to collapse tomorrow and erase us from existence. The magnetars lurking in our galaxy aren't close enough to scorch our skies. These things are real, yes, but they're also distant. And that distance is the only reason we get to sit here, safely, watching them from afar. We live in a calm oasis inside a violent universe, and for now, that thin margin of space is what keeps us alive. Space, it turns out, is still very big. The most dangerous star in our galaxy might explode, yes, but any minute in cosmic terms could mean tens of thousands of years or even longer, and if it already has, we wouldn't know. The light, or the silence, would still be on its way, crawling across the void toward us. Every time we look up at the stars, we're staring into the past. But that doesn't make these objects irrelevant. Pulsars, neutron stars, and magnetars aren't just strange curiosities floating in space. They're the universe stripped down to its raw mechanics. They don't follow comfort. They follow physics, pressure, collapse, spin, and gravity. The forces that shape everything from the tiniest atom to the fate of entire galaxies. These stars show us what happens when nature pushes matter to its absolute limits. They remind us that what we call normal, a calm sun, a stable orbit, breathable air, isn't the rule. It's the exception. Most of the universe is violent, chaotic, and endlessly powerful, full of energy bursting in ways we can barely comprehend, from objects we'd never survive being near. So no, we're not in any immediate danger, but yes, we should still pay attention. Somewhere out there, not impossibly far from us, a star is spinning itself apart, gaining mass, losing control, edging closer to collapse. And when it finally goes, there won't be a warning. And if you're someone who finds comfort in the stars, remember, not all of them are kind. Some are simply waiting for their turn to fall. If you enjoyed this breakdown and want to explore more deep space mysteries like this one, make sure to like, share, and subscribe. Your support helps keep these cosmic stories coming. Until next time, keep watching the skies.